Imagine you're riding your bicycle down a road and you realize all of a sudden that your brakes are broken. You can't stop your bike and you're headed for an inevitable crash. That's what happens when the cell cycle malfunctions. Cells divide out of control, and cancer is the result. There are 4 stages in the cell cycle: a growth phase, a synthesis phase, another growth phase, and finally, mitosis. But why does this system fall apart? Lots of genetic mutations can damage the cycle, but the mutation of one gene is both necessary and sufficient to cause cancer. This is the gene RB1, coding for the protein pRB. pRB plays an important role at the R checkpoint in the cell cycle, which kicks off the rest of the process. Just like airport security, pRB checks that a cell is safe to divide, stopping cells from continuing on the cell cycle until growth factors signal the cell to divide. pRB works by binding to E2F transcription factors that trigger DNA replication. When E2F is bound to pRB, it can't access DNA, so the cell doesn't enter S phase. But when the cell is signaled by growth factors, special proteins called cyclins add phosphate groups to pRB, and at the R point, pRB is hyperphosphorylated, unable to bind to E2F, and DNA replication begins, setting off the rest of the cell cycle. But if pRB is mutated or always hyperphosphorylated, even when there are no growth factors, it stops binding to E2F altogether. The cell cycle loses its master brake, spiraling out of control, and cancer quickly follows.
This discovery of pRB's significant role in cancer progression opens amazing prospects.
Scientists can now use malfunctioning E2F and pRB to tag the DNA of cells that are dividing out of control, so immune cells can find and destroy them.
This breakthrough could even lead us to a cure for cancer and put the brakes back on this runaway bicycle.